Okay, so this is the first video in chapter 11 for Thanksgiving break. So first, I thought it might be useful if we really talked about spring motion or simple harmonic motion in reference to a horizontal spring in more detail. Some of these equations, 11.4 through 5, 11.5 is really the most important one. They're not quite as important as some of the other things in the chapter, but it's a big deal to kind of understand simple harmonic motion from the basis of a spring. So let's just look at them in a little more detail together. Okay, so you can see we've got a horizontal spring and it's being analyzed at a variety of stages. So first, you have the spring being compressed a distance of negative a, then it's released, so it goes forward. You can see the little lines of motion, so it springs forward, it passes equilibrium, and reaches a at its farthest point away because of that initial compression. Then it bounces back and it goes back past equilibrium. Okay, so I really like the way they have the potential and kinetic energies displayed at each one of these different points in this spring motion. So that's really nice. Okay, so from before you should remember that for spring motion we did that back a while ago. The total energy is kinetic plus potential at any point, so let's just write that down here at the bottom. So the energy total is kinetic plus potential. So of course kinetic energy is always just 1/2 mv squared. You should remember that. And if you've got an elastic type of situation, anything with a spring, remember that potential energy is 1/2. It's kind of like Hooke's law, but it's got a 1/2. And instead of just kx, it's kx squared. Okay, so that's what we've got at any one time when we're in this one of these stages of the spring motion. Okay, so notice 11.4a. Why do they have that? So they're analyzing the motion at this spot right here. Okay, at point point A where the spring is being compressed. So at that point there's no motion because it's at rest originally, so no kinetic energy, it's all potential energy. One thing I'd like you to note is why are they calling this distance, like the farthest distance A and the farthest distance back, negative A? Well, the reason for that is because that's going to be an amplitude. If you've already read ahead, or if not, you can think about this as like it's originally down the farthest. This is like a negative cosine wave that this spring starts out as. So it would be like negative cosine, negative A cosine, excuse me. Let's make that an A. Negative A cosine of something. Can you imagine that? So let me just draw a little wave down here at the bottom. So here's your axis. Here's negative A. And here's positive A. And this harmonic motion is going to be modeled with cosines and sine waves. So since this one started out at time 0 down the farthest, it's going to be like a negative cosine wave. Can we imagine that? And then it's going to keep going. So this is the, then it pops back up to A, and then it can keep going for, as long as possible. So they're going to talk about that more further down the road, and they might have a video about that. But anyway, so this will be like a negative cosine wave with an amplitude of A. Alright, so that's why they're calling that A. It's for the amplitude of a cosine or sine. Anyway, so at that point, though, it's all potential energy. So you get energy is 1/2 k, and the distance x is what they called A. Okay, so square the negative, and there it goes. Okay, then the second part is where they're looking at this equilibrium position. At that position, like all the energy is kinetic. You might notice that. All the energy is kinetic. It's all because of motion. So the position at that spot is they said, well, we want to look at position 0, so that's why that's 0, so there's no potential energy. And the velocity is maximized at this spot because that's the spot where it's going to be traveling the fastest. All of its potential has been turned into kinetic. So anyway, that's how we have that one. Then they say, okay, what's happening at the end when it goes to its farthest position away from when it was compressed? So I think that once again here, you're going to have that's all potential energy, and now it's ready to start springing backwards and having a velocity again. So technically at this spot, notice they say the velocity is 0. It stops for just a brief instant in time. Okay? So again, we have the same thing would be right here. Anyway, so then it starts going back, and they say just pick an arbitrary x value somewhere between equilibrium and the farthest displacement. So they say at that x time you have, it's both part potential, part kinetic. Part potential, part kinetic. Anyway, so they say, how about we just solve for v in that situation? So let's look at what they have there a little bit. Let me erase some of this so we have some workspace. So what do they have here? It looks like in this equation they're solving for the velocity. Okay? So if they're solving for the velocity, what do they have? Well, first of all, the total energy, what did they set it equal to? Because it's got to be equal to something for them to be solving for this velocity. So what is this total energy over here equal to? Well, from this, let's see. So I think they're saying up here that the total energy is, you can think of it as the entire kinetic energy or the entire potential energy. So here's the total energy right here, and they're saying that's equal to, they just said, they picked the expression for when it's all potential, because at like this time you can see that the total energy is conserved. It's the same throughout this process. So one way to find an expression for it is to say, well, the total energy at point A is going to be the same as at 0, as at negative A, or at any point in between. So the total energy is going to just be the same as when it's just all potential energy. So that's why they've set it here. So in this equation, they're solving for V. So that's all they've done. So it looks like you'd first subtract this term to the other side. Actually, you know what? I would get rid of these halves first. So I'd cancel out these halves by multiplying by 2 across the equation, you know what I mean? Then I would add that to the other side, so, and divide by m. So let's do that over here off to the side. So in other words, v squared equals k a squared, right, plus kx squared, and then you divide by that m. So let's see if that looks like what they have. You guys see that? So these both share a k, so they factored the k out and put it over the m. And then that's exactly what we have, isn't it? Oh, oops. This was a plus. You guys see that? So this should be not a plus, but a minus. There we go. Now we have exactly what they have. So then let's see what they did on the next step, okay? So we've got this step right here. So now what did they do on the next one? Once again, I'm going to erase to give us some more space. I'm going to change color too. Okay, so what did they do on the next step? It looks like they factored out an a squared. So let's see how that goes. So you take out a squared out of that and you get 1. If you take an a squared out of this, remember factoring, when you take a squared out of this, it's really like dividing. So it's like you divide that too. Remember that's factoring that you guys haven't seen so much. But anyway, factoring is really division. So when you take a squared out of this, you divide by a squared and get 1. When you take a squared out of this, you divide by a squared and you get that thing divided by a squared. So there we go. Then we've got that. We take the square root. So you square root both sides. You get a plus and a minus because you used the square root. Remember, this is holding up with all math that we know. And there you go. So they say, hey, why'd they call this part right here V max? Well, because isn't what we decided up here, isn't V max equal, it comes from this. So if you have the total energy and its potential, this is what you have. If you have the total energy described as kinetic, this is what you have. They're equal to each other because energy is conserved. So if you solve for V max in this equation, let's just take their word for it, you get this guy. And hey, it turns out that V max from that little expression is equal to k m a squared square rooted. And look at that. When we were doing up here, that's what we got. So in other words, this term right here is just the max velocity. Okay? So there's that little expression. So the real big equation here, the only one you really need to be concerned with, this other stuff you should be able to derive without too much trouble on your own. But the one you're really concerned with that I'm sure you would have a little bit trouble deriving on your own is this guy right here. This guy is pretty key. It describes how the velocity of the spring is at any particular moment in time, so long as you know the max velocity, which you can get by just looking at equilibrium, and you know the value of A, which you get by just saying, okay, how far does that spring go in either direction? Okay, so that tells you the velocity at any time for the position x. So it'd be really nice to also think about this in terms of calculus. Can we somehow get an expression for x, the position, and then just maybe take a derivative and get this same thing? That would be a good way to confirm this with a more powerful, probably easier to understand technique. So I think if you scroll forward, I'm just going to scroll forward. If you haven't yet, that's okay. But if you scroll forward, let's see. What part is this in? I think it's way down the road in the chapter. Where is it? Let's see. I forget where it is. Oh, I guess it's not that far down the road. In 11.3, you have them talking about how x is actually a cosine function. So anyway, at some point you're going to show that x is like we talked about earlier, it's some kind of a cosine of something expression. So if you took the derivative, you should be able to get that too. But anyway, just a little bit of talk there. All right, let's use this to do an example. Okay, so 11.4, we're using this to do an example. So 11.4 says, okay, you've got a spring. It stretches 15 centimeters, I guess. When you put 3 kilograms onto it, then it's lowered onto it. So I think they're talking like vertically. So let's see what we've got here. I guess they're talking about this kind of a situation, right? You want to make this bigger. They're talking about this kind of a situation where mass is let go on the spring vertically. Okay, so you've got like the spring the restoring force of the spring expressed by Hooke's law with negative kx, and then you've got gravity trying to pull it down. So we're going to have to think about both those when we're trying to figure out what the spring constant is. Okay, so that's what they say to do first. Then they say horizontally it's pulled. So that's just like what we were talking about a second ago in that previous derivation. Okay? So let's just keep in mind that first it's vertical. We'll keep that off to the side there. So the first question is to find k. So like I said, we have to think about gravity as well. So let's apply Newton's second law in the vertical direction and say the sum of the forces equals ma. Since they just like let it go, they're not accelerating it, so that's going to be equal to 0. So what are the two forces that we have here? Well, we'll take, I guess, down as the positive direction, so we'll say mg, and then the opposite direction we have that restoring force of the spring, kx. I guess they called it x0 because that's just like what it is at the beginning. Anyway, so we can solve and say that we have, that's an arrow, not an equals. So we know that, I guess, mg equals kx0. So in other words, k, holy cow, that's getting bad. K is going to be mg divided by x0. So we say our spring is 0.3, so 0.3, 9.8. I guess I'm out of practice with this thing. And how far did they say it stretched when we let it go? We gently let it go and it went 15 centimeters. So we put that in our calculator and you get, I'm going to trust the book, 19.6 newtons divided by meters, spring constant. That's what kind of units you get. Okay, so 19.6. All right, part B says, what is the amplitude of the motion? Remember, this is after you've flipped it to be horizontal and pulled it this far from equilibrium. Well, doesn't that just basically say it? So what is the amplitude? Well, if you've pulled it this far from equilibrium, that's how far you've made the amplitude, so you're kind of controlling the amplitude and made it 10 centimeters. So that's done. Part C says, what is the maximum velocity? Well, remember that comes from thinking about energy being conserved at different positions. So the maximum velocity is, if we think about this as equilibrium and this as how far we've pulled the spring. Let me get rid of this now. Scoop it off to the side, I guess. So if we think about this part being equilibrium, kinetic plus potential, and this part being the farthest it goes, so here's the spring, here's equilibrium, and here's the farthest it goes. So at equilibrium we have no potential energy, and at the farthest the spring goes, when it's like starting to be restored backwards, we have no kinetic energy because it stops for a second. So anyway, you find the max velocity from that, so you just solve for Vmax. First I'd cancel those halves, and then I'd say Vmax is K squared divided by m square rooted. So I guess the square root of a squared is just a. So that's going to be k that we found from before, 19.6 over m. The mass doesn't change magically, of course. Square root that part, and a we said was 0.10 centimeters. So there we go, and that's 0.808. So velocity, we could check the units, but anyway, meters per second. All right. Then part D. Part D says, what is the velocity when it's at 0.5? So it's like, I guess, coming backwards at this point, like being restored, and right there, how fast is it going? It's not as fast as it's going right here, right? So maybe it's like half or fourth, or I don't know. I guess we need to find out. So it should be less than 0.808. Let's just keep that in mind. Okay? So for that one, we're just going to use the equation we came up with. We're not going to rederive it. So let's just put the Vmax in there, 0.808. And notice you're always going to be subtracting something, so in the equation you can also see that it's going to have to be less than the thing you started with. Anyway, so 1 minus, they said, that's halfway back, right? 0.505, so 5 centimeters. Square that. And A, what was A? Yep, the amplitude was we pulled it this far. Square that. Put it in your good old calculator, and you get, according to the book, 0.070 meters per second. So notice, we couldn't have just said it was half. I think that's real key. One of the questions in the reading guide talked about how, that's meters per second, holy cow. One of the questions in the reading guide described how you can't apply kinematic equations. Remember, that's because we have accelerations going on here because of the restoring force in the spring. So the acceleration is not constant. So hence, since the acceleration is not constant throughout this little journey that the spring is taking, you can't think that it's going to be like a linear change in velocity. It's some other kind of more complex change in velocity. In fact, it's trigonometric, which we've talked about how this is going to be described by sine and cosine waves. So anyway, just a little bit of extra there. E says, what's the acceleration maximum? Now you're going to see, we're going to talk in the next video a little bit about acceleration, but first you should note that how can we get acceleration from this situation? Well, remember how we did F equals ma in the vertical? Let's just do it in the horizontal. So if we think about how the sum of the forces equals mass times acceleration, well, what do we have here? We want to solve for acceleration, so we're going to say that's going to be forces divided by the mass. Well, we know the mass is just 0.3, so we've already got that part. Gosh, my writing is bad, sorry. So what is the forces? Well, the force here, remember, is the force of the spring. That's what I just said a second ago. So it's the restoring force. Let's not make it negative. Let's just say we're just taking the absolute value. So the force is what Hooke's law gives us, which is the spring constant, whatever that is for our spring, and we know what it is for our spring, times how far we've pulled it, the displacement of the spring. Remember, this is kind of what you have control over as a person. The spring constant is the spring constant. That just depends on what kind of spring you're working with. Is it a slinky or is it a car spring? I mean, it's going to be what it is. But you can control how far you stretch it, and that's going to decide how much acceleration is provided to the spring. So anyway, we had, what, 19.6? And for us, we decided to stretch it 10 centimeters, right? And we put this much on it when we did that. So that's the acceleration it's going to experience when we let it go. It is 6.53 meters per second squared. Okay, one more question with this situation. So it says, okay, wow, I don't know what I mean there. I must have meant to say the total energy. What is the total energy for the simple harmonic oscillator? In other words, the spring, right? In that previous example. So what is the total energy? Not the total E energy, I don't know, crazy. Anyway, so what is the total energy? So we just talked about a second ago how you could think about the total energy at any point throughout that because it's conserved, but it'd be nice to just think about like at the end or maybe at equilibrium. So I'm just going to say at the end. You could do it as at equilibrium too. But anyway, so energy total, I guess I'll put a subscript on there. Let's just think about it at its farthest displacement, so that's equal to half k times that farthest displacement, which we called the amplitude, right, squared. So that's going to be half, what was our spring constant again, 19.6, yep. And the amplitudes, we decided to move it 10 centimeters, so square that. And you get 9.8 times 10 to the negative second joules. Remember, joules are really just Newton meters. That's one way to break them down. So remember, this is let's just look at the units here a little bit. So the spring constant was newtons divided by meters. A was a distance. So distance squared is meters squared, and you can see that this cancels and you get Newton meters, which is, in other words, joules. Okay, so there's a little dimensional analysis check. Part B says, okay, what about a half the distance again? So they're interested in half that distance again, or half the amplitude, and what's the potential and the kinetic there? They should add up to the total that we calculated at the end because energy is conserved, right? So what is the potential energy at half the amplitude? Well, remember, potential energy was just half k x squared, except x is no longer a. So at half that, it's going to be half 19.6 times 0.05 now squared. Let's see what that is. I got 2.5, well, the book got, I should say, times 10 to the negative second. Let me do that on my calculator real fast, just so we can confirm that they're not lying about something. So it could happen. 0.5 times 19.6 times 0.05 squared. Yeah, you get 0.0245. So that's 2.5 times 10 to the second. Let's write that out just in case. So 0.0245. Then up here, let's do that one again too. So up here you get 0.098. Okay, so then what's the kinetic energy at half the amplitude? So the kinetic energy, remember that's of course just half mv squared, so half mv. Ooh, what is v? Well, we'd have to go back and calculate v from this previous part right here, right? We'd have to use this expression for v. So, oh, we do have v at that spot, don't we? Because that's for 0.5. So we already did that. Let's use that number right there, 0.0. 0.7. Ha, we'll do it that way. We could have also used conservation of energy, right? So, oops, here it is. We could have also used conservation of energy, but I'm trying to show you that energy is conserved. That was my point on this problem. So we'll go 0.07. I don't know if that's enough decimal places. But 1/2 mv squared. There we go. So 0.5 times 0.3 times 0.07. So I got what did I get? Huh. Oh, what was it? 0.07? Let's go back and check again. My number didn't come out. So it was 0.7. Whew. I was like, what the heck? That should be 0.7. There we go. Redo. 0.5 times 0.3 times 0.7 squared. Ah, that makes more sense. So I got, let's switch to green here, 0.0735. If you add that to 0.0245, what do you know? You get 0.098. So we've shown that energy works exactly like we thought it did. Okay, so there's the first video. Make sure you watch the second one. This one wasn't too hard. The second one is probably more necessary. So see you next time.